Okay, so in review question 7, looks like we've got a ideal gas process. So the figure at right or the figure below shows two different processes in which 0.14 grams of nitrogen gas moves from state 1 to state 2. I guess we just assume that we can treat nitrogen gas as a ideal gas in this situation. Let's call process 1 to 3 to 2 process X, and 1 to 4 to 2 process Y. And the question is asked to determine the sign of the heat transfer in process X. Okay, so process X 1 to 3 to 2. So if we're looking for the heat transfer is going to be related to the change in the thermal energy and the work done through the first law of thermodynamics. The change in the thermal energy is equal to work plus Q. So for a lot of these questions, there can be a particular set of steps you can follow to figure out these quantities. Typically, general process is to figure out delta TH and work before you can figure out Q. Of course, Q depends on both these quantities. So for the delta, I'll start with the change in the thermal energy. So the change, if we go back to defining the thermal energy as 3 halves nRT, that's equivalent to 3 halves small n times RT, or large N, number of particles, times Boltzmann constant times T. And this is also equal to both of these, nRTs and nkBTs are also equal to PV. So, excuse me. So for closed containers, that's where we keep N constant. So no molecules can enter or leave the container. Then we can write that the thermal energy is proportional to the temperature, because 3 halves N and R will all be constants, so there's a proportionality between the thermal energy and the temperature. And the PV is also proportional to temperature for closed containers, again because N and R will be constant from the ideal gas law. PV equals nRT. So if we hold N and R constant, R is constant by definition, PV will be the product of P and V will be proportional to temperature. So that means that the change in the thermal energy for closed containers, and that's why I should have, again, I'm going to assume this is taking place in a closed container, even though it doesn't explicitly state that. Maybe I can update that on the slides. So the change in the thermal energy is proportional to the change in the temperature. And to find the change in the temperature, I want to consider the initial PV value to the final PV value, because PV is proportional to temperature. So if I'm looking at this particular question, I can see here that so for process X, P final, V final is larger than P initial, V initial. So it starts at a P1 times 100, moves up to 2P1 times 100, so the volume of 1 and 2 are the same, but I've doubled the pressure. So if I've kept the volume the same and doubled the pressure, I would have to have increased, doubled the temperature. So once you've increased the value of PV, you've increased the temperature. So I can state that T final is larger than T initial, meaning there's a positive change in the temperature, which means there's a positive change in the thermal energy. We have increased the thermal energy of the gas. So we can state that delta ETH is positive. So that's our first step to this problem. So we've got the left hand side, so if we figure out the work and then figure out this relationship, we can eventually figure out what the answer to the question is. So for the work, you're going to be looking at the area underneath the curve. Okay, so in process 1, I'm going to split this up into process 1 to 3 and then 3 to 2. So in 1 to 3, that is a compression of the gas. So we're looking at this area here. So let's highlight this in purple. So I can state that this is a compression where the final volume is less than the initial volume. So I can state that the work 1 to 3 is and this is the work on, and I'm going to focus on the work on the gas. This is the definition is work on. So the work in 1 to 3 is going to be positive. So that's a compression, because I know that the V final is less than V initial, and that will be equal to the area on area of this trapezoid. But the area, the work done from 3 to 2 is expansion, and that area is going to be slightly bigger than the area from 1 to 3. So that includes the entire area under the curve. And I'll just draw these with little X's. It includes this area, but also all the area underneath the 1 to 3 curve also. So it's everything underneath the 3 to 2 curve. And that is an expansion. So the work done from 2 to 3 is negative. That's an expansion. Okay. And that's because VF is larger than VI. And I know that the total amount of work done, so the work done from 2 to 3 is larger, so the absolute value of work 2 to 3 is larger than the absolute value of the work 1 to 3. So this is 3 to 2, sorry. I made that mistake there too. So this is, sorry, 3 to 2. Sorry about that. So, yeah, 3 to 2 is negative, and its absolute value is it's larger because there's more area underneath the curve. So work total is negative. The net work done is negative. There's more negative work done on the gas in the 3 to 2 process than there is positive work done on the gas in 1 to 3. So if we think about our ideal gas law, the first law of thermodynamics. So we know that the change in thermal energy is positive. We have increased the energy of the gas by increasing its temperature. Overall, the net work done was there's more negative work done in 3 to 2 than there is the positive work done from 1 to 3. So overall, this work is negative. So you can ask yourself, so we have a positive change in the thermal energy of the gas, even though there's a net negative work done in the gas. So for that to happen, Q must be positive. And not only positive, but larger in absolute value than the work done on. So this positive has to first counteract all of that negative work, plus have a greater amount to increase the thermal energy of the gas. So we can also state that the Q is larger than the work on in this for process X. So it's definitely positive. There must be thermal energy added to the gas through a thermal contact in this overall 1 to 2 process in order for the thermal energy of the gas to increase with that net negative work done. So the correct answer is A. Zoom back out. Let's see the overall question.